Just juggling with my screen here. Give me 1 minute. So if I say slideshow, So all hybrid looks like today then. Are we streaming?
Yeah, it's streaming have started. Majority of
Okay.
them, they are online only now.
Okay.
Yep.
So just give me 1 minute. I think I may need 2 screens here. Share. Ignore. If I go slideshow, okay. Can you guys see my slides in full screen mode or not?
Yeah, it's visible, sir.
So should we just leave it like that? For some reason it's not working out in terms of. Let's see if I can make it work like this. Okay, can you all hear me now?
Yes, sir. Yes, sir, you are audible.
I have juggled now. Let's see if I can share the slideshow, share. Okay, this is better, correct?
Yes, now slides are okay, sir.
Okay. I think maybe still some issues going on, but let me get started. So welcome. I think I have the wrong set of slides. Just today is a bit crazy. I've stopped sharing, right?
Yes, sir.
All right, sorry about that. We are all set to go now. as soon as my screen shows up. So this is the right slide. So we are really towards the end, but there are some interesting topics that I would like to share today. So what we want to do is look at some advanced topics related to whole life carbon assessment. Um, okay. So what I'll do is we've already looked at yesterday we looked at module C and D. You had a guest speaker who spoke about BIM and CDE. We had an introductory session on EC3 where we gave you a live demo on EC3. We talked about low carbon materials. I think Professor Radagaonkar talked about circularity, and we again had a guest speaker discuss financing for decarbonization. Do you guys have any questions from, I think today's Slido is also not working. So if you have any questions, please put them in the chat. So the first topic that I'd like to cover today is on uncertainty modeling. As you know, we had talked about initially that when we do WLCAs, the data that we have is quite uncertain. There is a lot of quality issues, a lot of lack of data availability issues. We saw firsthand yesterday in EC3 when we tried to search for some EPDs for even concrete in India. We could not find many. In fact, there were some expired EPDs that were sitting there. So there is clearly an issue with data. So how do we address uncertainty in WLCA? The RICS standard provides a model which you can use to address uncertainty at the assessment level. Within EC3, yesterday we saw for each EPD, there is a model that they use and assign some uncertainty at the material level, product level. So when we picked up a EPD for EC3, for concrete in EC3, it provided an uplift factor. Some places it was 9%. We saw some EPDs with 11%. And I think there was one with even 20%. So basically, if the EPD gives certain GWP value, you are then asked to further uplift it, multiplied by 1.1 or 1.095 as we saw. But then if you don't want to do that at the individual product or material level, RICS WLC standard provides a method by which you can address uncertainty in your underlying data. So basically what WLCA RICS standard does is it allows you to provide contingencies to reflect uncertainties in the underlying data. So the standard that we have is incorporates contingency factors for both primary and secondary data. So the WLCA standard provides a comprehensive uncertainty modeling approach. It considers project phases, quality of carbon data, and accuracy of the project quantities when assigning this contingency factor. So it's a three-part uncertainty model in which you can look at and assign some uncertainty to based on the phase in which you are doing the assessment. So if you're doing it in the design stage, obviously some information still may not be decided or clear. So therefore, you can then assign certain factor to that. It also considers what kind of data that you're using for carbon. So carbon factors data. Are you using product-specific, plant-specific EPDs? Then the uncertainty is less in those cases. If you're using industry averages, there is more uncertainty, so it assigns a different factor. And then lastly, as I said, it also includes uncertainty in the primary data. So if your quantities, bill of quantities is not very accurate, it's early stage and you don't have maybe very detailed drawings and you've taken some assumptions and done some high level estimation, then for that also the model applies uncertainty. So the WLCA uncertainty factor, as per the RICS standard, should be applied to all standards. So our standard basically has three parts. We come up with an uncertainty factor, which consists of three parts that are added together. Number one is contingency factor for the project phase. Second is the carbon data uncertainty factor based on the representativeness and quality of the carbon data. So yesterday we were discussing, what if I don't have an EPD for India, but I maybe have for Europe? Can I use it? Or I have a carbon factor from another location. Can I use it because I don't have a carbon factor for this location? So the RICS standard uses this idea of representativeness or representativity, which means the data that you're using, how representative it is for this location. If it is not, then the uncertainty factor would be high, because there may be some variations. And then lastly, we have quantities uncertainty factor based on the expected accuracy of the material quantities data, or your BOQ. So these three added together give you the uncertainty factor, which you then apply to the final report when you have done your assessments. So let's look at part one, contingency factor. So an assessor must consider contingency for the project based on the uncertainty at the time of the assessment. We use default contingency factors, which are applicable to all elements and all life cycle stages. So to account for uncertainty and lack of detailed or complete information, the relevant contingency factors must be applied to all modules A through D before reporting: upfront, embodied, operational, and user carbon. So it should be applied to all carbon calculations that you do. There is a slightly different approach which the UK Green Building Council provides. They basically suggest an approach which uses tolerance ranges for carbon results for different elements at different project phases, which could inform this process. So essentially, the RICS standard goes by when you are performing the assessment, and then it gives you one factor which you can apply for all modules, whereas the UKGBC uses more of an elemental approach. So how do you pick the contingency factor? If you are doing the assessment during early design stages, which as per the REBA plan of works would be stages 0, 1, 2, then the default contingency factor to apply to all life cycle stages and modules is 15% or 0.15. Technical design and construction stage. So now obviously you have your design drawings or your construction drawings, and you are in either REBA stage 3, 4, or 5, the default contingency factor to apply to all life cycle stages and modules is 6%. Okay, and then post completion, which is really, it should be your actuals data, even though there may be still some discrepancies. We assume that there are no uncertainties at this stage because you know most of the information. So the contingency factor is 0%. So basically, this is your first table where you are performing the assessment. Based on that, you'll pick a number. So the second part, which is the carbon data uncertainty factor, is basically used to make sure that if you're using generic industry averages or some estimates of carbon factors from other locations, then you have a higher carbon data uncertainty factor. So use generic data in early design due to uncertainty in product type, source, and manufacturer. So let's say you are in preliminary design stage, you wouldn't know who is the manufacturer of the windows, for example, or the doors or the tiles. So obviously, in early design stages, there's going to be uncertainty. So generally, because it is known that in concept stage, early design stages, there is going to be a lot of uncertainty. We do not apply any carbon data uncertainty factor. We assume at that stage, the estimate is going to be a ballpark estimate only. But when we begin progressively refining design information, meaning refining data to more specific sources, and we start using EPDs, then based on the quality of that data, quality of the EPDs, we start to assign this uncertainty factor for carbon data. So if specific EPDs are unavailable, you will use the best available proxy or generic data with the limitations. So essentially, what happens is you are basically looking at generic data or proxy data, the uncertainty is going to be high. So based on all of this information, we basically apply carbon data confidence scores for the technical design stage onwards. Early design, you don't need to worry because we already know that it's going to be a very broad estimate. But when we are working with technical design stage, construction stage, post-completion stage, all of that, then we assign this uncertainty factor. So we assess scores for the 10 most impactful products by embodied carbon. Remember in EC3 yesterday, we saw that you could see impact by material in maybe a Sankey diagram or in other types of diagrams and reports. From your report, meaning your assessment, you need to pick your top 10 impactful products which have the most embodied carbon, essentially from A1, A2, A3, A4, A5, B1 through B5, C1 through C4, top 10, maybe concrete, steel, aluminum, glass, and so on. Then key product definitions for those materials will dictate how we assign confidence and uncertainty factor. Okay, I think my screen froze again. Okay, so this is the table from the standard. It's called the carbon data quality matrix. So you take your 10 materials, you come and look at where you fall. The scoring is vertical. There are 4 different criteria that you assess. So geographical representativeness has maximum of 10 points. So let's say you got a ready-mix concrete, you know the plant, you know the manufacturer, you know the product, meaning it is the best possible data and it represents your geography. So like I could find a ready-mix plant 10 miles from where I live. If that's the case, it gets a number 10. And then you have what's called the technological representativeness, which is maximum score of 12, in which we have 2 different sub-dimensions, look at technology and look at product specificity. So you basically need to look for the technology underlying the product and the EPD that you're using, and how specified or specific the product or data is. Highest score is 6 in each dimension. So if you have the best possible, very good situation, you can score a 12, 6 and 6. But if the EPD or the product that you're talking about partially reflects the technology and technical characteristics, the score will go down to 4. So using this table for your top 10 materials, you can come up with a score. I think the total is 40 points. Out of the 40 points, you're going to get a score. So you can use that list, come up with the score using this table, and then you will apply the carbon data quality matrix. So you're going to assess each product's A1, A2, A3 carbon data set for geographical, technological, and temporal representativeness. So the other aspects you have to look at is time, and then you have to look at data. Okay, so these dimensions are looked at. You evaluate any additional aspects which are listed in table 11, score each data set out of 40 with higher scores for more representative and verified data. So higher the score, better it is. Obviously, the standard actually provides how to score, the scoring methodology in table B2 and appendix B. Based on all these calculations, you're going to then calculate a confidence score for each product, weight each product score by its embodied carbon impact. So let's say you have 10 materials. Each material is going to get a score out of 40. Then you're going to find a weighted average. The weighting is done based on how much embodied carbon that particular material has. So that average weighted score is used to determine the overall carbon confidence score. It looks a bit complicated, but this is how it is. So you will look at your first product, and you will score 10, 6, 6, 8, 5, 5. You get a score of 40. Okay. Maybe there is another product which is using industry average. Then you give 10 for geography, 3 for technology, and so on, and scores 33. So you will score all your 10. You will then take a weighted average based on your embodied carbon contribution of each material, and then you will get an average score, which should still be out of 40. Then, once you have your carbon confidence score for the weighted average top 10 embodied carbon materials, you will then assign a carbon data uncertainty factor. So this is little, I think, unnecessarily complex, but if you do it in a tool like one-click LCA, it makes life much easier. And you basically then, if you scored, let's say 35 or 36, then the carbon data uncertainty score factor would be 1%. Okay, so now 2 dimensions are done. The last dimension is for primary data, which is quantities uncertainty factor. So the quantities uncertainty factor indicates the uncertainty in quantities used for WLCA. It must be assessed for during, again, technical design, construction, post-completion stages. Don't worry about it during the early design stages. Assess your quantity data quality for each of the 10 most impactful key products. So rather than going through every product in your estimate, you will again look at top 10 embodied carbon impactful key products. You're going to then calculate what is called the quantities uncertainty level, which is a score for each key product. Then you're going to weight and average QL scores based on, again, that embodied carbon impact to get the asset QL score. So 10 materials, weighted average using embodied carbon brings the QUL score for the project or the asset. Then you convert the QL score into a percentage, and you then add it to the previous 2 numbers, that is your contingency factor, your carbon data uncertainty factor. The 3 of them added together give you the WLCA uncertainty factor. So to calculate QUL, you will have to use some subjectiveness. So if your quantities have come from a BIM model, for example, they are highly accurate, they would be considered very good. QL score will be 0. This should actually happen post completion, because you would have your actual quantities. If you want to work and go and check your as built, let's say concrete, you have purchased concrete, you know the actual quantity. So it would be very good quantity information, zero QL score. If it is a zero QL score, you are going to get quantities uncertainty factor of 0%. If you are doing it during the quantities that you've received are through a design, measured, calculated, modeled averages, then QL score is 1, and therefore it would be 1%. Okay. Same for fair and sufficient. Obviously, if you have less confidence in the quantities of materials or bill of quantities, you will have a higher quantities uncertainty factor, like up to 4%. So, for example, you have a project, it is at the technical design stage. You have the full WLCA completed. Now you have to apply the uncertainty factor. You're in technical design. So if you go back here, the default contingency factor is 6%. So we pick that up. The 10 most impactful products or materials should be identified. Based on that, you will go and do the calculations from table 11. You will then do the average score using the weighted average by embodied carbon. And let's assume you get a confidence score of 23 as weighted average of all your 10 materials. So then you will, so you got this. 23 will give you 4% carbon on data uncertainty factor. So you get 4%. The quantity data for the 10 most impactful products, same calculations, probably in an Excel spreadsheet, your top 10 embodied carbon materials. You go and look at each one of them, then do a weighted average by embodied carbon. And you maybe find the average QUL score to be 1.2%. So then if it is 1.2%, the uncertainty factor is 2%. So if the QL score is 1.2, obviously from this table, you will get 2%. You add the three together, that is your uncertainty factor, 12%. So now you're going to apply that to all modules except B6, B7, B8, right? B6 is energy, got nothing to do with materials, done through an energy model or maybe through metered data. So no uplift required. You just use the number that you get based on your calculations. B7 is water use. No, it's not impacted by this calculation. B8 is user carbon. Either it's not calculated. If it is calculated, then you don't have to apply it. So basically in your final report, you will use 1.12 to increase the assessment number because of the uncertainty in your underlying data. Okay, so that's basically what I wanted to cover on uncertainty factor. I know this was a bit of a rushed and perhaps a choppy explanation, so I'm going to take a little pause and see if anyone has any questions or comments. Any questions? Okay, so in that case, let's move to the next topic, which is called biogenic carbon. So what is biogenic carbon? It's carbon removals associated with carbon sequestration into biomass, as well as any emissions associated with this sequestered carbon. Fancy word, but basically, let's say you have timber. timber stores carbon, sequesters carbon. So if you use it in your building for any use, then it should be calculated and reported separately. As you saw, as per our standard, biogenic carbon is reported, calculated, reported separately. When any biomass, for example, timber or any agricultural crops, enter the technosphere, in our case, when they enter a building, any sequestered carbon, which is called the biogenic carbon, contained or sequestered within the biomass, must be considered as a removal of biogenic carbon dioxide from nature into the product system in the module in which it enters the system. So if you decided to perhaps replace an exterior wall panel, which was earlier some lightweight concrete, with perhaps a wood panel system, maybe an interior wall. Let's talk about an interior wall. Then during B3, when this product entered your building or your system, is when you will start calculating biogenic carbon. So it must be considered at that time. And then end of life, if perhaps you send that timber beam or timber panel or wood panel somewhere else to be used, you're going to get the benefit of that recycling, reuse somewhere else in that particular module. But in most instances, it, let's say, comes into the system comes into the system boundary during construction, then you will account for biogenic carbon as upfront biogenic carbon in modules A1, A2, A3, A4, A5. And then when it leaves, you will calculate it in module C or module D. So the biogenic carbon, the sequestered biogenic carbon is normally, if it comes from timber, it should be sustainably sourced. And any other biomass must be considered to leave the product system boundary when it is either transferred to another product system through reuse, recycling, or recovery as a secondary fuel, transferred to nature when emitted through combustion. So maybe you just it gets incinerated, thrown into landfill, or any other composting, any other anaerobic digestion. You will consider emissions at that stage. So basically what's happening is when it enters your system, you get a credit for the carbon that is stored in the biomass. And when it leaves your system, then you basically release that carbon dioxide back if there is no recycling, no reuse or recovery. So if it's transferred to nature, if it remains undegraded in landfill after 100 years. The RICS standard uses a static LCA approach, so it doesn't consider the time value of storing the carbon. You don't get any credit for storing that sequestered carbon in perhaps a timber beam. So to calculate impact and removals of biogenic CO2, we assume when it enters your system, you get a minus or a credit 1 kilogram carbon dioxide equivalent per kg of carbon dioxide removed. Emissions of biogenic carbon have GWP of plus when they leave the system. So essentially it's a wash, -1, +1. That's the static LCA approach which our standard uses. On the other hand, there is one example. I haven't come across many. In France, they have a standard called RE 2020, which uses dynamic LCA technique, which essentially means you get the time value of money, or it's a time value of carbon. So this is an example from the RE 2020. It's in French. This has been there is a chat. I'm going to address that in a while. Let me finish this example. So we have, this is in French, so I have translated it. Maybe there's something lost in translation, but I checked with a colleague and they think that this is correct. So you basically bring in a timber beam, which has stored carbon dioxide of 600 kilograms. So you get a benefit of negative 600 kilograms of carbon dioxide equivalent for your system. Then you install it. Maybe you have to lift it. Maybe you have to do other things. You emit 30 kilograms of carbon dioxide equivalent during the construction process. So I'm looking on in the left-hand side of the table, which does the static LCA, which is what our standard does. Through the entire life, let's say 60 years or whatever number of years are allowed in France, there's no other emission coming from that element, right, from the timber beam. Neither it's adding more carbon or releasing or emitting more carbon or storing more carbon. So it's practically zero from, I guess it is for 50 years in France. So from year 1 through year 49, there is no usage emissions. That at the end of life, you basically send this system out, you're going to get a negative, sort of, you're emitting 700 kilograms of carbon dioxide equivalent, which basically means total life cycle for your system, for your building, is 130. In our case, it is zero. We don't give this end of life unless you add any demolition related emissions, deconstruction related emissions. If you assume 100 kilograms of carbon dioxide equivalent in your so if you look here, whoops. Okay. Yeah, this is not working today for some reason. You get my point though. I guess you all can see the pointer. So minus 600, you got benefit. 30 was emitted during construction. Then you sent this timber beam out, but before sending it, you spent another 100 kilograms of carbon dioxide equivalent was emitted because of deconstruction. So really, the total life cycle is 130 kilograms of carbon dioxide equivalent. Okay, so minus 600 plus 600 washes out. You use 30 for constructing and 100 for deconstructing. So your system got 130 kilograms carbon dioxide equivalent because of that beam. Whereas in the French standard, in dynamic LCA, you apply what's called weighting. So they say when you bring the timber beam into the system, the weight is 1, which is same. So you get a credit of 600 kilograms of carbon dioxide equivalent. Then you spend 30 kilograms of carbon dioxide equivalent for construction. So you get, again, weighting is 1. So you get 30, same as the static LCA. From year 1 to 49, there is absolutely no further emissions or removals. So you basically have zero, no change. But when this system leaves when the timber beam leaves the system, they apply a factor of 0.578, which comes through the dynamic LCA calculations for emissions. So only 404.6 kilograms carbon dioxide equivalent is released into the system. So released out of your system. So basically what's happening is you are getting a credit for storing carbon for 50 years. That net is a negative 165.4. Okay, so that's how dynamic LCA works. That's how basically your biogenic carbon works. Any questions on that? Did I confuse you guys, or does it make sense? Any questions? So more or less same thing is happening here. End of life, 600 is going to be released back because it was sitting in the in the timber beam. You spent 100 more for deconstruction. So still the total was 700, but it gets reduced. What you release back from your system into the environment gets reduced by a scale of 0.578, which means about what, 58%. So you are getting benefit of storing carbon of about 42%. Okay? Whereas you get a zero benefit for storing carbon in that timber beam for 50 years in the case of static LCA. Okay, so we're clicking through. I'm on section 3, briefly talk about grid and material decarbonization. But perhaps I got to take a pause and see if anyone has any questions.
Sir, there is one question by Harshal P in the chat section.
Yeah, sorry. Should have looked. Okay, so come here. For most of the construction projects, we don't have proper accounting of water usage, machinery operation time, or waste generated during. How can we account for them in calculation and uncertainty? That's an excellent question. Actually, to be honest with you, it's global and not just in India. But things are slightly changing. There are contractors in the US who are now trying to track emissions from all construction equipment. They're trying to track water usage. But in the absence of that, remember we had some thumb rules in the standard where you can just use a percentage value of what was done in A1, A2, A3 as an estimate for A5. So you still have some ways to make assumptions and do approximations. But I think there are a few things that I promised I will send, and that would be hopefully today. I'll send you the AGC Excel spreadsheet. It's like telling the site people that, hey, you track diesel, you track labor, you track equipment, you got to start tracking water use and fuel use and those kinds of things. So you probably can give them that Excel spreadsheet and have them perhaps even note down the number of equipment being used, number of hours they are being used, and so on. So there can be some stuff that you can do to overcome this. So the other question is about difference between static and dynamic LCA. The key difference is that the timing of the emission, when did that emission take place over the life of the asset, has no impact on our calculations in static LCA. But, and I'm going to cover this in a topic coming up, where we talk about time value of carbon, similar to time value of money. If you think about time value of money, right, you would know that you have, if you do the NPV calculations, how you can bring all future money's cash flows into today's money. Similarly, you can apply that concept, and that's what is part of dynamic LCA. They give you credit for number of years. I gave the example of biogenic carbon. By using timber, you are benefiting the environment because you're storing carbon in the timber beam in your project. Static LCA, because it does not give any benefit of when the emission took place. Did it take place 50 years from today, or did the emission take place today? They are all treated the same, whereas dynamic LCA treats it differently. It gives you credit for storing carbon. Yeah. So it can be applied, means that's the basic implication. So really, yes, it would apply to embodied carbon. We are talking about embodied carbon essentially. Abhiram, does that answer your question? Harshal, did that answer your question? Okay, I'm just going to assume silence means yes. Nature of construct, how can labor inputs be effectively accounted for within LCA? For labor, essentially what you're doing is you are only using for, it's an optional measurement within the RWLCA standard, and you're using the emissions that you're counting when it comes to labor is for their transportation. Yeah. Rest calculations are done for installation and assembly, and once again, you can use approximations there. Okay. So the next two items I want to cover is grid decarbonization impact. In plain English, what does this mean? It means that if you buy a unit of energy from the grid today, the emissions may be higher, but because the entire economy is being decarbonized, various countries are decarbonizing at various, at different pace or different speeds, but nevertheless, the grid is decarbonizing. So when you are estimating 60 years from today, should you consider that the energy that you purchase is as dirty or as less clean as it would be in 50 years? Probably not. So when doing this long range estimates for B6, which is energy use, B7, which is water use, B8, which is use of carbon, and then D2 for beyond system boundary, you can use these kinds of curves. This is specifically for the UK, produced by the future energy scenarios. So essentially, it's telling you electricity grid decarbonization over the RSP of 60 years. So you can see how the electricity grid carbon factor is going to change over time. That's the purple line. I don't know how clear it is. And average decarbonization factor is also shown in that orange line, the straight line, which is about 50. I don't know, I can't read that, but I think it is tons of carbon dioxide equivalent per megawatt hour, or whatever that number is. So for your WLCA calculations in the UK, you can use this number to essentially assume that the grid is becoming cleaner, the grid is decarbonizing, so this grid decarbonization factors can be used. I am not sure if such a chart is available for India. Perhaps one of you can check and find out. Similarly, materials that are being produced today, for example, cement, I think most manufacturers are trying to find ways, like if you go to Heidelberg, produces cement used in concrete. You go to steel, there is so much effort in green steel. Even the manufacturing process is changing and becoming more energy efficient. So how would you apply decarbonization of the materials? Obviously, this doesn't apply to module A because you're doing that today. So it's happening like year 1, year 2. It's not going to, technology is not going to change that much that you need to decarbonize, assume material decarbonization. So it's zero, no decarbonization for A0, A1, A2, A3, A4, A5. B1 also no decarbonization. B1.2, you assume 50% decarbonization for all predicted impacts. So similarly, you can use this table, but this is generally applicable to the UK, both for building projects and for infrastructure projects, how material decarbonization would work. Next, they are all connected, but they seem sort of advanced topics just put together. So next is time value of carbon. This, maybe I should have put this closer to the discussion of biogenic carbon, but nevertheless, it's here. This is actually taken from a colleague who has written an excellent article. The source is provided below. Francisco Pamponi in the UK has done an excellent job explaining this in very simple terms. So as you know, time value of carbon, I think all of you probably either study, research, or teach time value of money. Same concept sort of applies to time value of carbon. Now, we are saying that today our building produces X amount of emissions. Our goal is to, in 30 years, whatever, 50 years, decarbonize, become net zero. Now, obviously, you can choose to not decarbonize and then slowly decarbonize and still meet your goal. You can do a steady state and keep removing at the same pace and reach this net zero. Or you can be more active and you can remove at a faster pace, right? So this is that other curve. Why would you be incentivized to decarbonize faster? Because the end goal is the same. You were at 100 and you have to reach zero. How does it matter? You can just reach zero slowly. Maybe try and reduce most of the carbon emissions here, right? Why would you select a faster pace? Anyone want to take a guess? No? Anyone? Either in the chat window or in the classroom? So let's say you have, the longer the carbon dioxide stays in the atmosphere, more harm it causes. Sooner you remove it, the better it is, right? So from that point of view, it is useful to think about time value of carbon. It is still, most standards do not use dynamic LCA to account for timing of the emissions. So question really is, emissions here of 100 kilograms of carbon dioxide equivalent here, is it the same as 100 kilograms of carbon dioxide equivalent emissions here later in the time? So if you were just doing absolute reduction without any other sort of criteria to measure what you're doing, then obviously you should be slowly decarbonizing rather than. Okay. So do we need to break now? In 20, so I have 20 minutes. Or do we need to break? No, I'm sorry. I was just not sure about the time. No, we have about 15 minutes left, correct? Okay. So when you consider timings of the emissions, WLC typically treats all emissions equally over time, ignoring the timing impacts. As you saw in the biogenic carbon calculations, didn't matter that we stored emissions or carbon in the timber beam because it came at -1, left at +1, 60 years later. But the time value of carbon highlights that emissions today have greater long-term effect, right? If you release carbon today, if you emit today, it's going to stay in the atmosphere longer. So early carbon savings, for example, in embodied carbon, may be more valuable than future ones. Timing matters due to climate impact, technology evolution, and grid decarbonization. So it's a it can be seen from different sides. If you delay, then maybe technology will improve, maybe grid will be decarbonizing. So timing is therefore very important to be considered. Assessor should consider when emissions occur. Sequestration potential and energy context are crucial. Basically, if you want to go deeper into this, there is a report produced by Arup, which you can reference. In detail, it talks about 3 ways to look at it. One way is to look at it from what's called buying time theory, which is essentially delaying emissions may avoid them later. Static time horizon, earlier emissions have more warming impact. And then social time preference, that future emissions valued less than today's. So using these 3 approaches in a particular case, you can then identify which approach is better. Okay, so give me 1 minute. I'm going to see if I can find time value of carbon. Okay, back here, present something else, Chrome window, share. So you can see there is this paper. Okay, there is this paper written by, so you can go to this link. I'll maybe share the link with you in chat. And this paper, okay, so you're not seeing, present something else, time value of carbon, share. So this is that Arup report, which goes in a lot of detail. You will enjoy reading this. It's a bit technical, but you can, if you're interested, I'll again share the link, review this also. Okay. So it basically also references the RE 2020 regulations. If you go here, you will be able to also see, you can download RE 2020 also. Okay. So then something else, window. Okay, back to the slides. Okay, so considering timing of emissions, Current guidance advises against applying time weighting in standard WLCAs. So as you saw in our standard, because this is still a developing area, perhaps researchers can pay more attention. Maybe you guys already use it, but in practice, in industry, we are using static LCA. So the time weighting is not being considered. Use insights to inform specific decisions without distorting consistency. Material sequestration, consider timber's end of life using dynamic LCA if possible. So start small, maybe apply dynamic to timber. Then always try to do a trade-off between embodied and operational carbon. Assess payback of upfront carbon investments. Use grid decarbonization forecasts to assess future operational impact. Consider carbon storage value in bio-based materials over time. And then integrate timing insights. It will lead to smarter, more climate-informed design strategies. So currently, the standard doesn't use it, but you can still consider using it in your practice. Okay. The next topic I want to cover is UK net zero carbon building standard. But I think if we start now, I'll probably end up breaking this section, which I don't want to do. So maybe I'm going to stop sharing and see if anyone has any questions. And then when you come back from the break, I will start in the next section. Any questions? Related to what we have covered, or maybe something else? Yeah, so maybe we can take a break now and then come back sooner, or what's the best approach? Any of the coordinators there?
Yes, sir. Yes, we can take break now.
Okay, then we can start the next section when you come back.
Okay, sir.
Okay, so what time will everyone be back?
So in 20 minutes.
20 minutes, okay. Thank you. I'll be online anyways.
Okay, sir.
Thanks.
Hello, sir. Hello, sir.
Hello.
So we can start.
Okay. Okay. Okay, I think you guys can see my screen now. Okay, so the next section I want to discuss is basically, should we mute the, I think I'm going to mute this, okay. So the next section I want to briefly touch upon is the UK Net Zero Carbon Building Standard, UK NZCBS. These are not my slides, UK NZCBS slides, and they've given it to me. It's publicly shared by them, but they've given this for me to present. This is an industry-wide effort that has, I think for past 2 years at least, if I recall, has worked in the UK through the group of entities, including RICS, UK GBC. You've heard me talk about SIBC is there, iStruct-E is there, and BRE and other members. So these partnering entities came together and they created a net zero carbon building standard. This is where those targets and limits are set. This kind of comprehensive standard, I do not think exists anywhere else in the world. There are some jurisdictions who have started producing these targets and limits, but this is certainly a very detailed and very forward-looking standard, which is now entering into its pilot stage. And in the pilot stage, it will basically firm up a verification process, which I will briefly discuss with you, I guess. So the standard basically consists of a rule book. You can go to their website. It's freely available, download it. It is for, they call it sectoral, but really it is for all building typologies. So the UK Net Zero Carbon Buildings Standard, keyword buildings, is essentially not for infrastructure, but all types of buildings or major types of buildings, as you can see on the screen. It deals in both carbon and energy, and it is basically a science-based or science-led calculation. A very interesting piece of work, which perhaps you would be interested in following more details. I'll give you a high-level information on that. So the standard basically requires you to report and meet limits on upfront carbon, so embodied carbon. It asks you to look at operational energy in the building. You need to have start thinking about fossil fuel free buildings. You need to consider limits and targets for district heating and cooling networks, refrigerants, and any heating delivered. You have to report and meet targets. So you can notice the difference. There are two things: limits, upper limit, you need to stay below that. And there are minimum targets that you need to meet, such as on-site renewable electricity generation. And optional requirement is offsetting and renewable electricity procurement. And then for reporting only, they do life cycle embodied carbon. So this is a starting point. As you can see, they've gone one step. This is a great first step. You are required to do whole life carbon, but right now the reports, the limits have been set for upfront carbon, not life cycle embodied carbon. Um, and they require both energy reporting as well as operational emissions because of this grid decarbonization. So you want to make sure that buildings are actually becoming more energy efficient, and then they are also, when you look at the grid, they're becoming even more efficient. You don't want to just calculate and show operational emissions, because you may be gaining or benefiting from the grid decarbonization and not necessarily having buildings that are becoming more efficient. So the scope of the standard is all these building types. It does require whole life cycle approach, but it's definitely not applied to infrastructure projects. It's only for the UK, no other assets than buildings. And you have basically these types of buildings covered. So from homes, hotels, data centers, offices, schools, commercial, and everything in between. So good wide buildings typology inclusion. So limits have been set in this standard for upfront carbon, your operational energy, your fossil fuel, your district heating, refrigerant, and heating delivered. So how has this standard been developed? It has come together with, I think, years of effort by a technical group. That technical group took a top-down and bottom-up approach. So basically, right now, if you look at the Paris Agreement, or if you look at all those sectoral approaches, they very oversimplified explanation would be that you look at the GDP, look at the various sectors, look at the carbon budget that you have. A budget is essentially the amount of carbon that you can still emit and not exceed the Paris Climate Accord limits. So that is the top down. You can take from the whole economy to the construction sector. From the construction sector, you can then take it down to buildings and infrastructure, and then start going down. So you cannot just use top-down approach to set limits. You also have to do bottom-up analysis. So you have to look at building typologies. You have to look at what can be achieved at the asset level. And you will notice as I move forward that the limits are different for different building typologies, right? Residential construction should not have the same higher limit as maybe an office building. So how do you come up with that? You basically have to do top-down and bottom-up analysis in order to reach those right science-based limit setting tool, which is what has been used to come up with this standard. So here's an example. You can look at healthcare, or you can look at data centers. They are different. Performance spaces are higher. If you look at perhaps homes, they are slightly lower. The lowest is single family homes. And they also change by year. This is a much longer list. I've just taken the top few rows up till 2030. They have, I believe, up till 2050, all these numbers. So these are your EC1 limits, as they call them, the embodied carbon limits. These are upfront carbon limits for new works. So you are going to be basically using this, and the unit is kilograms of carbon dioxide equivalent per square meter of gross internal area, or GIA. So, and you can see pretty drastic reduction. Let's look at this number. See, in 5 years, it's going pretty low. For single family homes, also there's a significant improvement over time. Limits are going down. So that's how you basically use the UK net zero carbon buildings standard. Okay, so any questions on the UK net zero carbon building standard? I think several of you were asking me, what are the limits? This is an example of how a country has set limits. Okay, let's move to another topic called other considerations. Few things that you have to keep in mind, that we have this time dependent decision making over the life cycle of a project or an asset. So early on in your assessment, so let's say you're in the concept design stage, the ability to make an impact on whole life carbon is much higher because design choices are still open, products can still be specified, you can still make decisions that's going to help improve the carbon performance of your building. But at the same time, early on in the project, you would have much lower accuracy of your assessment. So that's sort of the balance you have to draw. But still, doing early cost and carbon calculation is very important. So if you're able to okay. So if you are able to work here, provide early cost and carbon advice to the client, it's very beneficial because the ability to influence whole life carbon is much higher. As you progress over time, practically it's impossible for you to, even though the accuracy of assessment is going to go up, but any changes made here, like in retrofit or during construction, it's not going to be having much impact on carbon performance of that building or asset. And also, moreover, you will not have, you may have higher costs associated if you are somewhere here and making a decision. Okay. So other things that I want to share with you are some illustrative examples from the standard, which talk about subsequent refurbishment in an asset. Okay, so let's assume that you have the life cycle of asset 1A, which has gone to 1B through refurbishment, and then you have another maybe demolition and a new asset created, asset 2. So if you focus on asset 1's life cycle of 60 years, or RSP of 60 years, it was basically, the asset looks like this. Asset 1A has been stripped out, partial demolition has taken place. You can see it here. And then new construction, and your 1B is becoming, so 1B gets constructed here, 1B gets used here, 1B's end of life, which means it's deconstructed, and a new asset 2 is created. So the standard okay, the standard does help you in assigning or allocating for various assets to their various modules. It tells you where which emission goes. So for example, if you look at life cycle of asset 1A/B within the site boundary for 60 years, the asset 1A will account for A 5.1. So whatever demolition that took place will go into 1A. And then 1B is going to have the second asset, which came up into being after the refurbishment. You will do A1, A5 from there. So then you will do the whole, this portion is the new portion. So the A1 through A5 calculations for 1B will be totally focused on this. But when the whole asset is back up, the 1B in use refurbished asset B1 through B8 will be for the entire asset, and so on. So the at least few possible combinations of how these assets connect to each other in on the same site is explained. Okay. The next is life cycle stages of an asset and successive interventions, where you can see that within the same site boundary, you have the first asset, you have your first asset, you have your second asset, and then another asset will come after that. So basically, how do you distribute emissions between these is explained. So obviously, asset ones, A1, A5 will have the construction of the first asset. Its in use will be B1 through B8, and end of life assets C1, C4 will remain here. So any D2, which is export of energy, will be captured in module D2. Now you're going to deconstruct, right? Some of it will get deconstructed. Asset, so A5.1 of asset 2, which is the demolition. Remember, A5.1 is demolition of asset 2. C1, C4 of asset 1, if they occur within the 3 years prior to the asset 2. So what it's explaining is this transition here. Asset 1 is going to get deconstructed. Asset 2 is going to get constructed. If this switch takes within 3 years, meaning the deconstruction takes place today, and within 3 years asset 2 is constructed, then A 5.1 of asset 2 will include all the demolition. The end of life, meaning any reuse, recycle, transport to landfill, and all those will be calculated under asset A1's C1 to C4. Okay. So similarly, when you do the next transition, you will see how various emissions get accounted for. So the successive new build projects over sequential life cycles are to be treated like this. The modular structure over 3 generations of an asset within the same property line are explained here. So interrelate, you want to make sure that you are giving credits where they belong, and you're showing emissions where they belong in the right asset. So again, something to consider. Okay. Now, reporting the constituent parts of a master plan. Now you have a large campus that is under construction. How do you do the various assessments? So there is an energy center, there is a refurbished building, there is buildings that are linked by a bridge, there is a building that is linked by an underground maybe tunnel or a connection, and there are some more external works. So basically, the master plan site, each building is going to be reported separately. So you're going to report. So you're going to report these buildings separately. You will conduct us. So these could be considered as sub-projects. These are all calculated separately based on the footprint at the ground floor, at the ground level. So you're going to divide up these buildings into sub-projects and account for them that way. It shows here the boundaries. These are your external works, which can be reported separately. So when you have a building that is connected by this underground structure, you're going to show it together. When you have two buildings that are connected by an above ground structure, you're going to report them together. So in this case, you have 1, 2, 3, 4, 5 building level assessments. You have a common facilitating works, which would be basically all the utility connections. You have external works sitting here, external works sitting here, external works here, external works here. This is your property boundary. So probably you won't consider this. You will only consider all elements that sit within these two red lines, which are your property boundary. So this is an illustration how in practice you will do the assessments. Here is a similar example for an infrastructure project. Again, these are your property lines. So these are the boundaries that you're considering. Here is your external work. Maybe this is a transportation network. You have a station building. It will be done separately. Another station building done separately. And then you have some sort of a tunnel with some maybe um, structure sitting here for above ground circulation, roof, and so on. These would be all measured, assessed separately. So the extent of work site boundary, this is your boundary. Above ground station buildings, bridges, and platform canopies calculated using building or infrastructure element categories as relevant and reported as sub-assets using the template that we provide, that RICS provided. Then below ground civil engineering works, tunnels, all cutting, all platform assemblies calculated using infrastructure element categories and reported as sub-assets using the infrastructure reporting template that RICS provides. So there are companies, there is practices who are doing these kinds of complicated assessments. And this, in fact, if you go back, if I go back, you will notice that this is actually provided to us by one of the authors, a company called Hawkins Brown. They are the ones who have produced these details. So we're using within our standard, folks who are experts and practicing have shared this information. Okay. Another thing, if you have a small project, we have slightly different requirements. You still need to do A1, A5. You still need to do upfront and life cycle embodied carbon. You can use predictive energy modeling if you have, for most projects, meaning large projects, you use energy modeling, but for a small project, you don't need to. You can use some kind of nomograph or some tables that can help you give a quick estimate rather than doing an energy model. Operational water is still required. There is really, if you have a small project, you know WLC comparisons between operational energy and embodied carbon may be needed. So you don't need to do that trade-off. Should I put a building element which is high in embodied carbon, low in operational emissions, or should I go for something that is low embodied and maybe over the years higher operational emissions? So that's the guidance that the standard provides for small projects. Another useful thing from the standard, I think we talked about scope 1, scope 2, scope 3 emissions from the GHG protocol. It explains, depending on who you are, depending on your role, how you will take these product stage, construction stage, use stage emissions reported under various modules, A0 through D, and how they will fit into your scopes. So if you are a product manufacturer, ready mix concrete plant, you are the one who's doing the assessment. Obviously, there'll be no A0. You will do A1, A2 calculations, and then that will go into scope 3. A3, which is transport from your plant to the site, is sort of debatable whether it's scope 1 or scope 2. Construction stage, because you are the product, you are the ready mix plant, you make send a transit mixer, you it's owned by you, so you can report the emissions. So it's not very clear, and that's what it's showing here, that it can again go into scope 1 or scope 3. So it can be supply chain or your own. A5 is all scope 3. So basically, if you are a contractor, you will report most of it will go into scope 3. Okay. As a developer, same situation. So this table helps guide where scope 1, scope 2, scope 3 emissions can connect or map to which life cycle stage. Now, why is this important? I think we discussed first day that if you're doing a company reporting for ESG or for any other carbon disclosure project, you are reporting at the company level. You could possibly use financial spend analysis or method to report your emissions. You don't need to go down to your asset level. Um, but as things are becoming more defined, you may be asked, you are a developer, you own 100 properties, you will have to go and do assessment of each one of those assets, do an WLCA, but then how do you combine all these and submit your report at the company level? This chart could possibly help. So I think there was a question. So if we want to assess for an educational campus, would it be owner occupier? Yes. So if you are, so this is basically telling you who's reporting. If you are the owner occupier, you are the campus owner occupier, you will use this row and report more or less everything into scope 3, right? Because a contractor is going to build the building, vendor suppliers will supply the materials, subcontractors, labor contractors. So it's all supply chain. It's all third party, your downstream folks who are doing the emissions. So it would be reported under scope 3 for you as the owner occupier. But notice B6, B8 are different. B6, you're going to buy the energy, you're going to pay the energy bills, you may have an on-site facility and so on. So it goes either be scope 1 or scope 2, depending on the source of the energy. And then B8, user carbon, which is optional, could either be scope 2 or it can be scope 3, depending on what life cycle stage you're looking at. Sorry, what kind of transportation arrangement do you have on campus? So that would be how you will use this chart. Okay. If we do not have information of that would be odd, right? Means your gross internal area, you should be able to calculate. If it's an existing building, worst case scenario, you go measure. And we have taken function unit as a yeah, if you have an absolute number without knowing per square meter, it's going to be tough to compare benchmark and baseline. But I don't know under which situation you will not have a GIA. Because you should have measurements of your building, right? Do you agree? Abhiram, do you agree? Yes? Okay. All right. So last thing, is artificial intelligence, AI, and sustainability. Okay, how many of you are using AI? This one I really want to know. How many of you use ChatGPT every day? Okay, one thumbs up. Wow, pretty much looks like everyone is coming alive. Yes, using ChatGPT. Do you have the professional version or do you use the free version? Paid version or free version? See one hand raised, so go ahead, Abhiram. Free version, okay. Anyone else using ChatGPT or a similar tool? All right, so I, I am obviously experiment DeepSeek. Wow, okay. I haven't tried DeepSeek. I'm a bit concerned about my data and privacy. How much does ChatGPT or a similar thing cost per month in India? It's $20 per month here for us. How much is in India? Anyone? Nithya, you said you're using professional. How much does it cost? Oh, it's $20. Okay. All right. So the question really is, can we apply AI to sustainability in an intelligent way and benefit from it? I think yes. It's already being used in construction. You have now most AI-enabled tools in construction. I would want to say US, but I think India is progressing equally fast. So the way things are happening right now is that a project manager on a construction site would come and give a prompt and say, hey, where is the elevator on my project essentially? So the AI tool goes, searches for drawings, BIM models, looks at Microsoft project schedule, looks at your emails, looks at WhatsApp, whatever information you've allowed ChatGPT to access, it accesses, and then it comes back and reports that you have the elevator should have been here last week. As per the updated schedule, you sent an email to the vendor on Friday. The vendor responded with a few new delivery dates, which means it's delayed. Would you like the co-pilot to update the schedule? So this is real stuff. It is happening now. You can give all your project data and get a chat bot or an assistant who can help you answer these questions. So how is today it helping AI is helping sustainability? You have chatbot interfaces to your BIM models, for example. So you can actually write a query and say, give me all columns in this building on level 2. And then you can say, give me the quantities for that level. So that chat interface is helping go search for the right information, go call tools which can do the calculations for you, and then provide you with the answer. So AI is helping in a big way. I did a little example. I basically uploaded in my ChatGPT a 2D plan. You can see a simple plan of residential unit, and then said, hey, can you please provide a table that shows the work breakdown structure and put the information in these columns, assume this as the start date, and do all calculations. So it can actually do the calculations for area calculations like here. So it read everything. It read everything here and basically analyzed the floor plan right in front of us and gave this information, which is accurate. You can use today AI on construction sites through something called a digital twin. So dust control, water leak, noise pollution, all those things can be measured through sensors which are embedded on the construction site. AI tool goes and searches for the right information, searches through all the edge data, does the analysis, and presents you the result. So this is on a Canadian construction site that they have deployed. This is an example from Canada. There's a company called Latium Technologies which has deployed this tool. We all know that computer vision is actually quite mature in the construction sector. You can take videos, analyze those videos. You can search for waste. You can search for um, essentially safety violations. There are companies who can now, you can go on site, take pictures of waste, of materials, of progress, and it can tell you, even do calculations in terms of sustainability measures, if there is rework, how much waste is going to end up in landfill and how much emissions that's going to cost. So there's a lot of work that's happening on AI and sustainability. This is an example from a company called Materials 2050. This is basically ChatGPT helping. So you upload the image of your wall and you're basically asking ChatGPT, GPT-4 to look at this assembly and create a table of, so in Revit, you have that feature called create parts, right? So it's essentially going to go look at these parts. It will calculate the quantities, and you're giving it 1 square meter basically, and then it can calculate the embodied carbon emissions. Okay, so it comes back, and this is actually still sort of a prototype. It is able to calculate these materials, their quantities, and it can actually go search for EPDs, bring back the right emission factors, multiply, and give you these numbers. Okay. Future state is going to look like this, again from the same company. It's essentially what's going to happen is you will no longer in few years run software tools. You will just open up a chat interface and you say, okay, I want to write a letter or write an email. Here are the key points I want to cover. You don't need to open Outlook. This AI chatbot will open Outlook, draft that email based on the instructions that you gave, and then it'll send that email, or at least save it as draft and say, hey, go check the draft and are you ready to send? Because human in the loop is still crucial in AI right now. I don't think we have reached a stage where we can let AI do everything on our behalf. So it's called HITL, HITL, human in the loop. So there are various use cases in sustainability that can be applied, but for at least companies who are exploring the use of AI, they should use some kind of a framework to evaluate whether it makes sense to use AI or not. So if you were to create an interface to search through thousands of EPDs, make it much easier to provide that AI interface or a chatbot interface, it probably makes sense. So the way we think about this is consider 3 dimensions. Consider the complexity of the use case or the problem. Consider the additionality of AI, and consider the data availability along those 3 dimensions. So essentially, look for complexity. If you're solving a problem, you don't want to use AI to solve low complexity problems. Try and search for high complexity problems. And then look for additionality, meaning if a human can solve a problem easily and AI doesn't add any value, you don't want to really do this. So do not take use cases or applications that sit in this zone 1, meaning low in complexity, low in additionality, and there's less data available, you're not going to get the gains that you're looking for. So here is what you're looking for: high data availability, high additionality, and high complexity. That probably is a good zone. So I think sustainability, WLCA, material selection, design options probably would sit somewhere here. So they are good candidates for applying AI. I do see a hand go up. Abhiram, do you have a question? Well, it says open queue. Should I click on open queue? Chat. Do you want to put it in chat, or do you want to, Abhiram, do you have a question that you want to, you can turn on your mic? What about accuracy? Good question. Okay, so that was a legacy hand. When you say accuracy, you mean the accuracy of the output, right? It is still a challenge. Hallucination, as it is called, is still a problem. So ChatGPT can make up stuff, but it's improving, increasing tremendously. From where we started a couple of years ago to where we are today, I think there's lots of improvement that has taken place. So accuracy has increased, but it's still not there. That's why they say human in the loop. Okay, any other questions moving forward? This is sort of the framework we think would work for construction, including sustainability. So looks scary, but it's pretty straightforward. What AI helps us do is you can take all your data, all your project information, not only current project information, but information from all types of projects, historical projects also. And you can store it in a knowledge base or a data store or a data lake. So information from models, from drawings, from IoT sensors, from videos, images, email messages, files, whatever you can think of, PDFs, and so on. You can take both structured data and unstructured data. So Excel spreadsheets, PDF documents, everything. You can take information from current project, if it's an asset and you have meters, sensors, you can collect all that data. You can have data from past projects and assets. You can get supply chain data, market data, regulatory data. Then through what's called extraction, chunking, and embedding, you're going to create something called a vector store. This vector store is then ready to be used alongside your large language model or AI. So the user gives a prompt. That prompt gets embedded, sent to this retrieval source. It's called retrieval augmented generation. So you ask a question, it goes and looks at not only what is available in the LLM, but the knowledge that you have provided, which are specific to your project, maybe a database of EPDs, a database of LCIA, and many, many similar things, material quantities. It's going to now not only use the features of LLM, but will also go search for information that is closely related to the question that you, the user, has asked, and then come back, combine that prompt, that the question that you gave, plus the context it found from your standard operating procedures or whatever else you have stored, then combine that with, it's called the context. So the question and the context then go to the AI model, and that AI model then gives a better response, and the accuracy increases, and also it is now domain specific, company specific response that you're receiving. So you can use this for anything. These are some possible use cases for this application of generally in construction, but you can apply it to sustainability also. Okay. So what's happening now is people are working on something called compound AI, which is multimodal. So it can use sound, video, images, text and that's called multimodal. So you can, let's say you have an asset that is running, you can go take pictures, you can bring sensor data from or your meter data. All of that can go, and this can be treated by this multimodal AI system, which can has various components, and it can help you answer better. So it's not just a chat GPT interface, it has multimodal ability in the back end. The next big thing that's happening right now is called AI agents. So people are moving to the next level. They are now creating AI agents that can do work on your behalf. So you can create an AI agent that is an expert in searching EPDs. That agent can work on your behalf, go to the internet, go to your company's database, and search for the right EPD for you. Then you can have another agent that is an expert in doing embodied carbon calculations. So you train that agent to focus on one specialism, one area of the WLCA. And then all of these agents can work together to give you a support system when you're doing LCA calculations for a complex project or program. So that's where all of this is headed in terms of research and application in sustainability. So basically, we feel that sustainability is one of the key things that AI can help solve. But then there is a flip side to it also. More the AI we use, as they say, one Google search or a chat GPT prompt, you spend 7 times more energy in the chat GPT prompt, and I think similar amount of more water for cooling of those GPUs that and data centers that are running somewhere. So there is that interconnection between climate and use of AI for sustainability, but we still think that AI can help in a big way in addressing climate crisis. You can use it to help solve other wicked or complex problems, such as delivering social outcomes or social aspects of sustainability also. So it can help perhaps address that user carbon that we always consider as an optional. It can bring in other aspects, such as if I use low carbon material or locally made material, am I generating more employment? How else can I improve the social outcomes of my projects? And then obviously, broadly, AI can be used to solve our construction productivity problem, which has direct implications or indirect implications for sustainability also, because if you waste less, you have less rework, obviously your environmental sustainability performance will also improve. So that's the way we think AI is moving forward. And there is some early evidence. Project Management Institute really has done an excellent study. I believe in April 2025, they released this report, which is called Sustainability in the Age of AI. So I think free to download. Get it, look at it. It's amazing what they have done. So they say that the leaders, 31% of the leaders are responding that they are very successful or extremely successful in implementing AI aided sustainability projects. So the AI is becoming a tool to help sustainability. Organizations, 40% respondents showing steady progress with moderately successful projects that are using AI to drive sustainability. And then obviously, there are few companies who are not too successful. You will see sustainability and AI success from ESG, environmental, social, and governance aspects. You can see some key indicators like people are using AI to do biodiversity management, which is an important aspect of sustainability in the built environment. From a social the point of view, their enhanced community engagement, and then human rights or social outcomes. So if you look here, it is the leaders are 45% report carbon dioxide emissions reductions when they're using AI. So it's helping them drive benefits directly related to ESG. Sustainability further, if you take this from the PMI report, the number one application area, whoops. So the number one application area is energy management and sustainability, which is good news, supply chain, and so on. So clearly you're seeing the benefits of AI usage in sustainability. Okay, I think that's pretty much what I had. Let me check. Yep, so let me close this. Then I'm going to do a little bit juggling, so give me 1 minute. Okay. So now I'm going to give you a live demo of AI tool that I'm building for sustainability. So let's see if I can share this with you. There are multiple screens involved, so just bear with me if you don't mind. Let's see what happens if I share my second screen. Are you guys able to see it? Thumbs up? Perfect. Okay. So basically, this is a pilot that I've created. It's going to be a bit challenging because I have 3 screens, but this is an agent-based system that I've created in which the agent I have trained to understand our 220-page WLCA document. Okay, makes sense? I got to swap this in order to make it more. Sorry for the juggling. Is it better? Can you see my screen better now? Yes? Okay, thank you. So basically this Python code that has been written. I'm using Google's agent framework. So let's see, we have created a chat interface, essentially our own chat interface. It's going to not know the outside world. So if I asked any question that you would typically ask ChatGPT, it won't be able to respond because we are controlling it to only work internally for us and be a specialist on our WLCA standards. So I can say, hi, who is there? Whoop. Let's see if it works. Looks like, yep. So this is Google's platform. I can say, what is the corpus name? There are any documents. Can you see the text as I'm typing? Okay. So it started working now. This is the agent responding. So the agent now comes and tells me, yes, there is I am the WLCA agent. I have some documents. I can say list the documents in WLCA agent. Whoops. Okay. It is going to get, so yeah, it basically says that I have the whole, like I've uploaded basically the whole PDF document. It's 220 pages. I've fed the 220 pages to this AI agent. It has learned what it is stored in there. And now I can start asking questions. So I can say, who is the main author of this document? Let's see if it finds out. So RAG stands for Retrieval Augmented Generation. So it goes, queries, and it finds out that Simon, which is correct. Did Anil contribute? Okay. I did contribute as the expert working group. Let's see. Okay, so I did do something and I was acknowledged. It figured that out. What is the price of concrete? So it's going to go look in the document. It tells you. So if it was Chat GPT, it's going to go search and give you some number. Here it's going to refuse because it does not talk about, the document doesn't talk about it. We've trained this agent to only focus on whole life carbon assessment. So let's start making some meaningful questions now. Can anyone suggest a question we can ask? I am in the technical design stage. what is the, what was the name of the, was it the contingency factor? Okay, let's see what it says. %6. So it was correct. So we found out 6%. What is the RSP for a bridge project? 120 years, that is correct as well. Let's throw some tricky question. Can somebody give me a tricky question? I see something in chat. No, nothing in chat. What should we ask it next? Let's test its intelligence. What is biogenic carbon and how do I calculate it? Yep, so I think it has come back with the right information that is in the, that we just discussed. How do I assess small projects? Let's see if Abhishek, if it can understand that. So it is basically giving you what I just had explained earlier. It's even telling you that what is considered a small project. And then you are saying, does WLCA use dynamic LCA process? Let's see if it understands that. So it does not explicitly say that it uses dynamic LCA process. It talks about RSP. Next question was, which LCA method WLCA follows? Okay. Um, so it does come back with a reasonably good answer. We can go and say, how do we allocate benefits and impacts from deconstruction, recycling, and reuse across multiple asset cycles? Maybe we should have said, but let's see what it thinks it is. It basically is able to pull that information up. It seems it is pretty good. over multiple generation of assets on a single site, so it has picked that up. What is the waste factor? Yeah, it has basically pulled up even the table for waste factor. Any other tricky question anyone wants to throw at it? And I could basically then also add the Excel spreadsheets. I can add all other remaining documents. I can upload my slides that I used during these sessions related to WLCA, and it can utilize all of that to give better answers. Right now, it's only speaking from that 220-page document. So pulling up table references is pretty impressive. Yeah. What else should we try? Can you optimize the BOQ for reducing cost? This is a question for, I don't know it will understand, but let's see, can. Okay, maybe before that, let's say, how can I use a BIM model to perform WLCA? So as you can see, it is churning. Yep, it has come back with the right answer. Okay, you talked about what is, let's see if even understands. Yep, it knows what it is. What is it used for? Technical design. How is post-completion assessment done? Based on this document was done, practical completion, post-completion, as-built model, as-built material quantities, benefits and load in usage based on expected performance. No, don't use any contingency factors. So it's giving you a pretty good, robust answer. What is grid decarbonization? Yeah, it is giving future energy scenarios, picked up the right stuff. Let's do material decarbonization. Expected reduction, yep, so it has picked up the right stuff. Let's throw a tricky question at it now. I am transporting 100 cubic meters of concrete from a plant to my site. I have not tested this before, so this may not work. The travel distance is 10 miles. Calculate A4 emissions. I don't think it will be able to get the answer, but let's see. Yeah, it can only give, because I've not given it any external tools, it can do the calculations, but it's telling you what to do. So search for carbon factors per ton kilometer, 10 miles. So it's giving the steps, but it doesn't give. Therefore, while the document provides methodology, I cannot perform the exact calculations using the information and your input because, yeah. All right, I think now we have reached a point where you all get the idea what this is. I'm going to stop sharing. So if I gave this a link to this to you guys, would you use it to learn WLCA? Okay. Great. So that's all the material I had to cover. I'm here to answer any questions. I know we have time left, so I'm happy to stick around, answer any questions. I think we have a quiz coming up today. So hopefully you'll all do excellent in that. And then is there a site visit? What's planned for the rest of the day?
So after this, there's a talk
Okay.
because we do not have too many participants like attending the session physically. So
Okay.
that's why instead of site visit, there's another company. Dr. Mangesh has some connect, so she is now giving a talk, and then
Okay.
post lunch we will have exam and then feedback. That's it.
Okay.
Yeah.
Brilliant. Excellent. But I'm here if you have any questions, because after that I will be probably, given the time difference, not available.
Yes.
But
Yes.
I'm here to, anyone needs anything, please feel free to reach out. Maybe one of the things I can do is share my LinkedIn profile. Whoops. Here is my profile. Thank you so much for details showing us what.
Hope I can
Thank
share
you.
your
Thank you
email
very
address.
much.
Can I share your email address with all the participants? If they wish, they can write.
Sure, yes, absolutely. I've shared my LinkedIn profile.
Okay.
I'm also, you can message me on LinkedIn. Do reference that you're from the Gyan program.
Okay.
Yeah, and you can share my email, no problem. In fact, let me put it here if you want. Okay. So my LinkedIn profile and my email is here. I'm again, this agent, I need to stop. It's still doing some work behind the scenes, looks like. Okay. Any questions, anything I can help anyone with? Is anyone conducting research in this area? Anyone looking at dynamic LCA?
So at VNIT itself, sir, we have started working. So one of my scholars is working, and in fact, he also delivered a talk, Mr. Sriram.
Okay.
So Srirang has been working with a lot of LCA related activities with chemical industries.
Okay.
However, now I have asked him to shift the focus for the construction materials.
Okay.
So what are all technologies or tools we have developed? He is working on Open LCA, and very soon I'll come back on that. I'll keep bothering you for the kind of work what we are progressing. Let's see how it works.
Absolutely. Anything you need, happy to help.
Yeah.
And anyone from this group needs anything, if you're doing research, if you have students who are doing research, I'll be very happy to help
Yeah.
in whatever way I can.
So very soon, sir, I will just request you maybe next week if we can have one quick meeting with some of the faculties here, because Honorable Director during inauguration he said,
Yeah.
let's plan
Yes.
out something on a larger scale. So we want
Yes.
to hear you, and then I can just give some brief about what we people are doing here, and let's see if
Absolutely.
something can be bridged in between, right, sir?
Yep. And if there's anyone in the department doing AI related work, maybe we
So
can extend this sustainability agent, make it much more smarter, give it even some other data and tools. So I've written some tools. Basically, what an agent can do is one tool it can use is the LLM. So in this case, it's using Google's Gemini. But we
right,
can make other tools. So we can add another Python tool which will say, okay, go get the carbon factors from the UK government's website. So
right.
whenever this kind of a question is asked, it will not just give you the instructions, it will actually perform the calculations and come back. So I think that's where this is all headed. Imagine in the hands of a practitioner, this kind of a chatbot, they're doing an assessment and they have a question, rather than flipping through 220 pages, they can easily use something like this and get the right answer.
So for AI, I will come separately because we just recently like signed an MOU with IC Impact,
Okay.
and hope you must be aware about Professor Banthia, who is from Canada but who also hails from Nagpur. So
Okay.
yeah, so he is hardcore into like concrete technology. So for UHPC as well as 3D printed concrete, we are working something on AI,
Okay.
and he's more into the durability aspects. So we are also coming up with new center for dam safety. That is what the core area of research of our director as well. So I am looking only for the material part. So,
Yes.
so prediction analysis, what we have done for the kind of health monitoring of the existing dams with the
Yeah.
images, satellite images. So
Hmm.
using, so I have few PPTs, so I will share it in person, and then let's see how we can
Yeah.
improvise. Yeah.
And I don't know, maybe you guys are already working with Esri
Yes.
or ArcGIS people. I can introduce you to some folks here in the US from Esri
Great. Great.
who are actually doing a lot of AI. So they can take a satellite image and we were talking to them, in fact, if they
Wow.
can look at the image of a urban center and count the number of cranes.
Great.
So then we can say how much construction is going on. So
Mhm.
every 6 months, they can count the cranes and you can see whether the market is hot or is
Yeah.
it cooling down. So
Great.
there are so many applications we can do.
Perfect. Uh,
So there was one question from Puneet, which I think maybe I should answer if you don't mind.
yeah.
I think the one major blind spot where India falls short compared to global is something that clearly calls for deeper research. I think India is, was quite impressed. There is somebody who's an architect who started the India LCA initiative. So I think she's from SPA. So good stuff happening there. I don't know. I think Rahul, you should connect with her. I'll try to make the connection.
Yeah.
She's doing some building projects also.
Mhm.
And then I think as part of the Mahindra Life Spaces, for example, is doing an embodied carbon project. I mean, they're doing calculations of embodied carbon on their projects.
Mhm.
Recently, Google and Tata Realty together are doing something using our standard. So there's a lot of activity happening on the practice side.
Mhm.
I think on the research side, we need a lot more data. You need product category rules, you need EPDs, you need more LCA research. And then I think just in housing, for example, with so much new construction, it's so crucial that we pay more attention to these aspects. So I think there is so much potential. I wish I was there physically. I had actually arranged so many meetings and other events, but
No worries.
as
So let's
luck
hope very soon. We look forward this
soon.
year at least one visit where I can come down in person and meet wherever you will be in India, if possible.
Absolutely,
So
absolutely.
let's hope.
I will plan certainly.
Exactly.
Um, So yeah, means I think deeper research into materials, which Professor Ralegaonkar is doing already, deeper research into LCA methods, deeper research into digital tools, AI, BIM, and those kinds of things are needed. There's a lot happening. I think Viraj presented yesterday
Yeah.
on BIM and CDE, the role of industry foundation classes. I think all of that has so much potential. It is, I think, very uh, lots of opportunities for practice, for research, and further study. Okay, so
Yeah.
I think with that, at least I can close.
Yeah.
The skill set we should develop by working in the sustainability area. I guess broadly, you're going to have data and analytics skills. If you have AI, that's even wonderful. Maybe do a certification on LCA. There are a lot of LCA certifications available if you're interested in that area. Other skill sets, I think, if depending on where you want to go, if you want to go into the industry, picking up on ESG and carbon reporting, like CDP is a carbon reporting framework, SBTI, Science-Based Target Initiative. There's something called CREM in Europe, CRREM. Having understanding of those frameworks is hugely, hugely needed in the industry. So if you're looking for a position in the profession, then those areas. And then I think research, obviously, there are similar areas also. All right. Well, thank you, everyone. I really appreciate it. Dr. Ralegaonkar, all your colleagues and the research scholars. I know how much work behind the scenes went into this. And the most impressive thing for me was the timeliness and the punctuality of all sessions. I think that's really very, very good. I hope we can continue the collaboration and do some more work together. And I hope to see you all soon.
Yeah. Thanks a lot, sir. And then I'll be also sharing one kind of format, or because we need to submit to GAN office the foreign experts feedback.
Sure.
So let me check if there